Well, thanks for the invitation again. I'm George Sklivanitis. Gonna be talking about a topic that I think we've been hearing all day today. I'll try to stay out of sensing and focus more on wireless and tell you what we have been doing at Florida Atlantic over the past few years. But before a small introductions, we started a Center for Connected Autonomous Systems and Artificial Intelligence back in 2020 with some fellow faculty. It's quite a diverse group, including machine learning researchers, folks from ocean engineering. Myself, my background is not an acoustician, it's not an ocean engineer. I'm an electrical engineer that has been focusing in wireless communications in contested and congested environments. It just so happens that during my bachelor's, I was doing a lot of work with wireless sensor networks, mesh networks, and IoT and software-defined radio technology. This is basically programmable radios. And the buoys that you see over there actually was what I was working on in my PhD. These are not SOFAR buoys, these are Teledyne benthos buoys. And if you've ever worked with them, they are a big pain. So, so that's what basically motivated us to start working on our own software-defined underwater acoustic modem that I will get in a bit. But before that, a little bit about the vision behind the center, which we thought was pretty timely back in 2020, and I think it's more timely now, really started from this idea of building connected, networked AI systems, right? So far we have been looking at AI agents that have been trained and tested as a single agent unit. What has been really missing in the research work, but it's really now picking up, it's really that aspect of connectivity and networking to apply AI. Either you are swimming below the surface of the water, or you are in the ground, or you are in the air, or in space. So there are multiple projects in the center, primarily funded by the Air Force Research Lab and National Science Foundation, as well as other sources, focusing on how do we establish this autonomous, resilient, and secure machine-to-machine communications in these challenging environments where you might not have any infrastructure. You might not have cellular, you might not have satellite, and that's the case when you are under the surface of the water, right? The two other pillars in the center are focusing mostly on the AI piece. I'm not going to talk anything about that today. But we are really interested and have very good talent with internationally acknowledged algorithms in the center, and we are doing pretty well what we call data curation. So anything related to filtering, denoising of your data before you use this data to train one agent or multiple agents, and of course, once you train your agents and you deploy them in the field, you care about monitoring for potential anomalies and things that might be going wrong during operation, right? And to do all this, you want to do that on software-defined programmable platforms that combine communications, computing, and sensing in a single platform. All right, you don't want multiple platforms. Below, you see some of the platforms that we get to work on all the way from underwater, surface vehicles, into robotics, programmable radios, millimeter wave radios. These are radios that are operating at higher frequencies. But let me jump into the core of the presentation today, which is informing you about the current status of wireless, which is pretty much what was 20 years ago. As some of the previous speakers mentioned, electromagnetic waves can work underwater. However, they can work in very small distances. Optical waves can get you a lot of data across, but they suffer from severe scattering. You have to align well your lasers. There have been visible light modems out there that have been doing pretty well in clear water, and where we are in Florida, we have to go in pretty big depths to make them work. So acoustic seems to be the best option. However, you still have some limitations. You have long propagation delays, limited bandwidth, high path loss, and here are some cares I took of a textbook showing you basically this trade-off of data range versus range, right? So as you go higher in range, you are losing in data rate and you fall down to bits per second. On the right, I believe, included what is considered the state of the art in terms of commercially available off-the-shelf modems from different companies. And with the two circles over there, you see basically the two different generations of the modems that we built at FAU. The first one is more of a lower rate version, more robust, and the second one is targeting this true high throughput video communications applications for shorter ranges. So the open problems that we are currently working in the lab is really creating this idea of truly dynamic, adaptive communications underwater, which we have been seeing in the terrestrial world, but underwater, it has really been all about fixed frequencies, fixed bandwidths, and not really this idea of truly cognitively adapting to the channel conditions, right? So if we can do that, then we can build truly smart and truly intelligent mesh networks, as one of the previous folks mentioned in the audience, that can be dynamically routing information from sensor to sensor. And we want, of course, to do that securely. So as I mentioned, the motivation behind building our own modem was really that it was super tedious to be working with these Teledyne modems. So we took the principles of a software-defined radio that's working in radio frequencies, and we transferred this in the acoustic world, and we built this small size, weight and power acoustic modem. It's small enough to fit into micro AUVs. It's low cost so that it can scale to tens or hundreds of vehicles. To give a sense of cost, the buoys from Teledyne cost about $25,000 each. These ones are about $1,500 with all the fabrication material costs. They are built around what we call a system on a chip platform that's provided by Xilinx. This is a Zinc system on a chip platform. It's interfaced with off-the-shelf hydrophones. You can use any hydrophone you like. The specific hydrophone we are using is pretty wideband. It goes up to 200 kilohertz. So we have the flexibility to go in ultrasonic ranges that would get us more bandwidth. And they are future-proof to support multiple channels as well as other type of modalities like optical interfaces, because we have built-in wideband ADCs and DACs. These are some specs of the Gen 1 modem. As I said, this was a lower rate modem, up to 2 kilobits per second, 64 frequency hops, adjustable frequency bins and bandwidth. And the Generation 2 modem was built on the principles of orthogonal frequency division multiplexing. This is basically what your Wi-Fi uses. So that has given us much more bit rate, about 345 kilobits per second, that can support compressed video streaming underwater. And you have the capability to adjust your center frequency and bandwidth. Some of the challenges underwater, in the underwater acoustic versus the radio frequency world, which many of you might not have seen again, but you have to deal with much lower propagation speeds, and that creates many problems with respect to Doppler. When things are moving, your signals are getting much more distorted. You have severe multipath. Your typical bandwidth with respect to the carrier frequency, it's much smaller, so you are considering the ultra-wideband cases, and the noise is not only electronic, but environmental, as we've seen from the previous talks. And on the right side, you see some spectrograms demonstrating this brutality of multipath. So the two left spectrograms are showing what happens when you have our modems in a loopback with a wire, and the two right spectrograms are showing what happens when our modems are actually communicating over the water. You can see the effects of the multipath. This is a pretty overloaded slide, but what it says is basically that we are developing a full stack from the physical all the way up to the session layer to support truly distributed autonomous cross-layer wireless networking to realize this idea of mesh ad hoc networking underwater. And what we are doing in the lab specifically, both in the radio world as well as underwater, is we want our physical and network layer as well as our transport and session layer, to be dynamically adaptive with respect to whatever our modems are sensing, right? So if somebody, for example, is trying to jam the communications between our modems, we want our physical layer to be able to dynamically switch to a different frequency or a different waveform to avoid this. But if somebody is also trying to inject traffic in the form of a denial of service attack in our network layer, we also want to be able to sense that without having to reflash our modem with new firmware, right? So what we are saying here is that in the wireless world, both in the radio and underwater, we have to do this jointly across all these layers. Moving on, this is a slide talking about how we will secure communications underwater, and it will not be with the public-private key cryptography that we have been using above water. So this is a technique that we have been working jointly with the NATO Center for Maritime Research and Experimentation in La Spezia, where we have demonstrated that two underwater acoustic nodes can basically use unique features of the underwater acoustic channel to get a private key generated on the fly, right? So you don't have to preload any secure key to any of these two modems. They can just talk with each other, use the features of the channel that will be reciprocal, or if they are not reciprocal, they would reconcile eventually to the same key, and then use that key to encrypt your communications. 1 minute. So this gets us to why we are here today. We are part of the Pioneer program. We received the developer kit, and we started working towards that vision of creating a bristle-mouth native underwater acoustic modem. But before we do that, we went the easy way of getting a Raspberry Pi interfaced with a hydrophone and basically recreating what we've seen in the previous talks. So I'm not going to spend much time on that. This is showing that this works. So moving forward, these are some of the projects that we are really excited about. We just got a new project funded by the National Science Foundation to develop this group of AI biorobotic fish. This is in collaboration with an ocean engineer at the center who is building this bio-inspired propelling vehicle using a single undulating fin. Basically, you see here on the top, the software buoy will be used as our gateway to be able to get the data out of our little school, our little group, as well as being able to remotely connect to them and control them. And on the bottom side, this is a collaboration with an NGO at the city of Pompano Beach and University of Miami, who is building this artificial coral reef breaking wave structures that are in the water. What we are doing for this project is we are having a bunch of sensors measuring water quality, as well as monitoring the fish populations that are starting to increase in the water, and running some nice AI computer vision algorithms to classify and detect the different species of fish. And with that, I will close, and I hope I didn't go much over time.